So this morning, while I was preparing for this lesson, I was thinking a lot about how math is very similar to theology in many ways. And the way we think about math is is very similar to the way we think about God. Because the same God who made theology, the same God who made the Bible, is the God who made math. Let me explain. So oftentimes when we don't understand what we're doing in math, we run into a lot of errors. So, for example, if you have um, in college algebra, it's really not uncommon for people to say, well, 3 plus 5 equals 8, right? They'll say that. And then we say, yeah, yeah, right, right. And then you say, and then they would come back and say, well, but 3 squared plus 5 squared does not equal 8 squared, as I thought. And you'd say, well, yeah, 3 squared plus 5 squared does not equal 8 squared. And they would say, well, there's a problem with math then. 3 squared plus 5 squared should equal 8 squared. Well, no, no, it's not that at all. A lot of times when we go into math, we see things that seem like contradictions. It seems like a contradiction because it seems like I should be able to add 3 and 5 together and get 8. But it's not a contradiction because the person who's saying this just obviously doesn't understand squaring well enough. And that's why it's so important when I try so hard to help you understand the intuition behind ideas and not just the rules. Because if you know the intuition, then you know, oh, well, 3 squared is just 3 times 3, and 5 squared is 5 times 5. And obviously that can't combine to be 8 times 8. That's not how that works. That can't, because that's just not the way numbers can even work. And so you can kind of get the intuition behind that. And so I hope that when you get these intuitions, that really helps resolve a lot of errors you could possibly make, because you'll click with it. It'll make sense. It makes intuition. But it's the same thing with theology. A lot of times, we often, if you go to college, you'll probably, and especially if you go to a secular college, you'll probably hit an argument from a philosophy professor, and she'll come up and say, well, the Bible says this and the Bible says that, but those two things contradict. Therefore, the Bible is inaccurate, and God may not even exist. And when that happens, I want you to remember, like, look, just because things can seem contradictory initially, it doesn't mean they actually are. It often just means you don't understand it enough. A philosophy professor, when he's trying to talk about theology in the Bible, is speaking outside of her expertise. Her expertise is philosophy. That's what she's educated in. Like, for example, even a English professor could make a math mistake as simple as this, because she just doesn't practice math. She doesn't think about it all the time, so it's possible for her to make a mistake as simple as this. And similarly, with a philosophy professor could make a simple mistake as well. It looks like God says, "You shall not kill," and in the Bible, and we say, "Oh, yeah," and then you would say, "Well, God also told the nation of Israel to go wipe out a whole nation and kill everyone in the nation," and we'd say, "Well, yeah," and the philosophy professor would say, "Well, God's inconsistent." No, God's not inconsistent. You just don't understand how God is working through Israel as his representative. And so when he tells the nation Israel specifically, go destroy this nation, he is saying, I am wreaking judgment on that nation. They have sinned, and they've sinned greatly, and I'm sending the nation of Israel to go act as my representative to destroy them, or to discipline them at least discipline them for their deeds, because oftentimes he does spare them, at least for just a little bit. And so that's kind of the idea of what's going on here. I just want to help you understand that, because it seems pretty easy for teachers, especially even teachers like myself, to speak outside of their field of expertise. My field of expertise is Bible, and gosh, man, I make so many mistakes when I try to teach physics. Don't teach the physics student. Don't tell the physics students that. But anyway, I hope I found that really helpful for me to know that there's that important distinction there. Just because someone knows a lot and they're a professor, it doesn't mean they're an expert in every field that they speak of. So a philosophy professor can't talk about the Bible so well, and an English professor can't teach mathematics. They can't teach those rules. Anyway. So today's lesson specifically is really cool. I think you'll find a lot of fun things in it. We'll just go ahead and jump right in. Make sure you have your unit circle. Those are things that are really nice to have. And we are going to look at these following ideas. We're going to talk about specifically complex numbers and how complex numbers work, and the really in-depth understanding of how to use complex numbers in a really cool, I think just fascinating way. How they combine, how they multiply, how they divide, how you can take them to a certain power, and then we're going to try to even help you re-understand your idea of the number 1 and what does it even mean for something to multiply to 1. And that's the kind of depth we're talking about. This is the kind of depth that people would think is that's just stupid. Multiple things multiply to 1, not just it's more than just 1. Well, yeah, there's a lot of things that multiply to 1. Anyway, we're gonna get into that. So let's start with the basics. Let's start with some simple definitions, so we are clear on what we're talking about. Okay, the first thing we want to talk about is simply what is a complex number? What is it comprised of? What is it made of? Well, we've talked about before, we've said before, that a complex number has 2 parts. There's a plus bi. We say that there is a real part, and then there's another part that we call imaginary. And again, imaginary isn't the best word, but we use imaginary to kind of represent the idea of the square root of -1, of how it's kind of an imaginary-ish number. It's just as legitimate of a number as any other number, but it seems weird and nebulous, so we call it caught on the term of imaginary. Okay, we also talked about a while ago about how to graph a point like this. We talked about how if we wanted to make a number line, say this is a number line, we could make a graph of this. Let's see, 1, 2, 3, 2, 2. Okay, and we could take a point, say a point right over here, and we could draw a line to this point, and we could say, let's see, if we were to graph this point, we have to graph it on a Cartesian coordinate plane. We can't just plot it left or right. We've got to use a 2-dimensional space, which is really cool. It really helps us understand what's going on here, because things are kind of rotating instead of just moving up and down or left or right. Anyway, so we've got the real axis, which is also, basically what A is. It's the A axis. We plot all the A on it. And you have the imaginary axis, and that is the BI axis. So if this point right here would be, I suppose, 3 plus 4i, because we are 3 across on the real axis and 4 on the imaginary axis. So 3 plus 4i is what that would be. And so we said we could take these things. We could take this point, and let's call this point something. Let's give it a name. This imaginary number, a plus bi. Let's call it something. We can call it, and for the course of this lesson, we're going to call it one singular thing. We're just going to call it z. This is the name we're going to give it. Name, I suppose. So we'll just call it z. And so this is point z, or in other words. And when we try to graph point z, we can see a couple interesting properties about it. Okay, so let's look at this here. I could say, if I want to find the distance from the origin to z, that's this dark green line here, or I guess light green line. We would call that, we've called it a bunch of things at this point. We've called it, if this is a point, we've called this a radius. We've called it, the magnitude of the vector z. We've called it a ton of things. Let's kind of break that down what this is. This is, if we have z, we will call that, we can call that distance. Actually, we'd call this, you often use these double lines to represent it. We would say that this is z with those double lines. And again, we've used a couple of different tools to talk about this. We said this z can equal, this can be the magnitude of vector z. This is something we've talked about before. Or it's just z. You don't have to use the you could say just z instead of just vector z, because this is vector z with the arrow above it. It's vector z. We've also called it the absolute value of z. So absolute value of z. And in this case, because this is not a vector, we're more prone to call it this as opposed to magnitude. because this isn't, we're not calling this a vector. It's not a magnitude vector. But there's other things that we can call this. And it's this weird term. I tried to figure out why it's called this. I couldn't figure out exactly why it's called this. But here's another term we can call it. It's called the modulus of z. This is the modulus. So using two important terms. The simple reason is because we're now dealing with things that are like in this, we're dealing with a lot of points now. We're representing points not just with a plus bi, but we're using something called polar coordinates. And polar coordinates, they like to use this term called modulus instead of radius, what we're used to. So we could call it the radius as well. And so radius is fine. Radius is fine. You could call it radius. Or the fancy term, which you'll probably often see in your book, is its modulus. Okay, we have that. We also have something else that we can represent with this. But before we get to that, let's kind of break down another way to write this term. We're used to writing this a plus bi in this form, and that's all well and good. It works. But let's write it in a slightly different way. Remember, this is, if we use this is like plotting x and y. And I go x units to the right to plot A, and then I go BI units up to plot BI. What if I wanted to plot this complex number using polar coordinates instead of just rectangular coordinates? What if I want to use it polar means? So again, this is the rectangular version. This is the rectangular form. And again, we call it rectangular because it's like when you graph x and then y kind of like makes half of a rectangle. So we call it rectangular form. But polar form, let's convert this to polar form to see what we can do with it. Now I hope you remember what polar form is. To get to polar form, let's just do right down in the corner how to get to polar form. We would say a, let's see, to change a or x, so a equals x, and to get x into polar form, we would take the radius times the cosine of theta. Radius times the cosine of theta, whatever this angle is. And so we'll take this. So if we want to find x or a, remember we go a to the right, and we go bi up, and we would say a is the same thing as saying the radius times the cosine of theta. That was the formula we used before. If you were confused as to why we use that, I would recommend going back to the old videos and seeing if you can kind of get the intuition behind it, because that's important. And then bi is similar. It's b is just y, or just the radius times the sine of theta. So we'll say bi is the radius times the sine of theta. Okay, cool. So, except if that's b, then if we have bi, if we go bi, then we have to say radius times I times the sine of theta. So that'd be radius times the I. Let's get to the right color. I times the sine of theta. Okay, because we're going to bi, not just b. So let's make sure we get that clear. Okay, so now if I'm adding these two things together, we've got the a part, and we're adding the bi part. So if we have a plus bi, that means that instead what we have is, let's see, a plus bi then, a plus bi would equal the radius times the cosine of theta plus the I times the radius times the sine of theta. Okay, and then we can use a quick, we could factor out an r really quick from this, and we can get r times the cosine of theta plus I times the sine of theta. Cool. And this is a way to write a plus bi in a form that's, well, the polar form, the polar coordinate form. And so here's how that looks. We can say this equals radius times this would be let me make sure I get this right, cosine of theta plus I times the sine of theta. Great. And this goes by a bunch of different names, and it's kind of hard. There's no really official name for it. So I've called it polar form just now because it's a lot like the polar form of anything, the polar forms we've used before. But you could also call it, and the way the Pearson-Prentice-Hall calls it, is trigonometric form. So much homework often says in trigonometric form. So you want to remember that's the terminology we're looking at here. Another form that's pretty common that's often called is modulus argument form. So modulus arguments form. And some people just call it mod arg form. It goes by a bunch of different names. The name you probably should know, but the name is probably most helpful, is that trigonometric form. That's the one that you're really going to want to make sure you get down. And so we kind of see what the modulus is. We said, well, the modulus is the radius. We're in that radius form. But what's the argument? Well, the argument is actually pretty straightforward. We talked about how there's a radius, and we also need a theta. Theta is the number of degrees it is up from just going straight right. So radius is that. So this would be the theta. Did I say radius is the number of degrees? I'm sorry, theta is the number of degrees it goes up. So theta then is simply we're used to calling that the angle, but now we will call it the arguments. There we go. So theta is the argument in all of this. Great. So maybe it's better to rewrite this again just to make sure that we've got it clear. Because all the things that are in blue are probably things you should probably want to make sure you know. This is new information that you want to make sure you have down. So in the same way that x equals r cosine theta, we're going to say that a equals r cosine theta. And we're going to say that bi equals, let's see, I times r sine of theta. Just to make sure that that's really clear. That's new information we haven't really talked about before so much. We kind of just discussed it though. Okay, so those are the major definitions we need to know. Those are the major tools we needed to really get going here. Now from here, we can figure out the rest. And here's where we're going to get to the next part. The next part that we need to talk about is what's called operations. I'm going to make a nice line down here, a little partition. The next part is operations. What can you do with this information? How is it helpful? What can we make with it? So let's go and start with an imaginary point or a complex point and see if we can figure out some useful tools from this. We've already multiplied complex points together before, but now what we're going to do is we're going to try to multiply complex points together with polar form or trigonometric form, more accurately. So let's go ahead and name a point. We'll say we'll have a point. Let's call Z1. Let's call that a point, and we'll call Z1 just the exact thing we just wrote up here: r cosine theta plus I sine theta. So that'd be, I'll use R1 for it. R cosine theta, R1 cosine theta. Use theta 1 because this is the first point. Plus I times the sine of theta 1. So that's Z1. Z2 will be the same thing, just because we're going to make this, I want to make this as clear as possible. I'm declaring these two variables as new things. Z2 would be R2 cosine theta 2 plus I times the sine of theta 2. Okay, great. What can we do with this? Well, we can do a couple things. The first thing I want to show you how to do is multiply these two things together. So we're going to talk about multiplying. Now, before I go ahead and just multiply it for you, I want to give you an idea of the intuition of what's going on here before we get to the algebra behind it. Let's kind of go to, I'm going to quickly switch over to Desmos here. I can get rid of that. Desmos here. And so I want to give you an idea of what this means, what's happening. To give you a kind of frame of reference, I've made 3 points in Desmos. The first point is just a given point in polar form of this complex scheme. So we've got, this is the complex plane, we've got the real axis and the imaginary axis, and the blue line is our first line. The green line, actually the green line is the third one. The red line is our second line that comes out, and the green line is the product of those two lines. Those two lines multiplied together. So let's kind of see what happens when we multiply these two lines together. Right now, you can see the radius. You can see the radius of line 1 is at 0. The theta of line 1, that's the number of degrees. So I'm just declaring radius, and radius isn't theta. Radius of theta of 1 is 0 degrees. The radius of line 2 is 0, and the theta of line 2 is 0. Okay, let's see what happens when we start adding things in. Let's say I set the radius of line 1 to 2. All right? And then I'll take the radius of line 2, and I will make that also 2. And you can see the green line, the third line, shoots up to 4 when I do that. Similarly, if I was to bring the radius of line 2 up to 3, you'd see the green line shoots up to 6. This is interesting. So the radius of the green line, in this case, when it's still flat like this, is just the first radius times the second radius. And that's kind of how we've been used to it. We've seen this before. We've seen when we multiply polar coordinates. When we did, one polar coordinate times another polar coordinate. It was the same kind of thing. It did the same thing. Okay, and if I went on, radius 2 is 4, we get 8, and if I made radius 3, 3, it would go all up to 12. So that's really kind of how the radius works. It's really baked into the identity. Well, if we're going to multiply two polar points together, we're going to multiply the radiuses. That's essentially what we're doing. We're taking the radiuses, and just like any other point, any other scalar, any other number, if you take 2 points and multiply them together, then it'll just multiply. That's what we're doing. So all radiuses, when they multiply together. That's really cool. So if I want to multiply 2 polar coordinates together, if I want to multiply 2 imaginary coordinates together, this is actually makes it a lot easier than trying to do a plus bi times another a plus bi and do the foiling and then work it all out and do I squared and all of that, and that takes a lot of work algebraically, but this is really more elegant. It just says if you take 2 radiuses, you just multiply the radiuses together, and then you've got the new radius. The third radius is those radiuses multiplied together. Or I guess I'm saying radiuses. I actually mean radii. Okay. Now let's say we did something different though. Let's say I made 2. Let's say I brought it back to the radius 1 to about 2. I guess it doesn't matter so much. And then I make radius 2 about, let's say I make that about 4. Okay. Now let's try something else. Let's say I try and I change the degrees. Maybe I'm a perfectionist, but I like making these exact numbers. There we go. Okay, I'm going to change the degrees of the first theta. So I'm going to take the first angle, the blue line, and I'm going to start bringing it up. And you'll see the green line follows it. Whenever I bring the blue line up, the green line goes straight up with it. So that's interesting. So if I make theta 1.93 radians, it'll go straight up just like the theta of the green angle, the product angle, will be 0.93 radians. Same thing if I do, now let's see what happens if I add, so it doesn't matter what I do, I can bring it as far around as I want to at all, and it'll just follow that blue line. Interesting. Now let's take the second one, the red line, and see if we add that in. I think this is cool. You're gonna like this. If I take the red one and I start adding that in, it also brings the green line up the same amount. Both the red line and the blue line control the green line. If I add more to theta of the blue line, it'll add to the green line. If I add more theta to the red line, it'll add to the green line. That's interesting. So with normal numbers, if we multiply them together, what we do is we multiply them together. But thetas are angles, they're degrees. We can't really multiply them in the same way we can, when we say multiplying those, we can't just multiply them in the same way we can multiply a number or a scalar or something that you plot on a number line, because degrees you don't plot on a number line. You can't plot a degree on a number line. It's something different. So when we say we multiply the thetas together, we're actually saying the way these things multiply together is the way they combine like this, the baked into their identity is just adding. It's what they do. They add together. You add the radius, the theta of the first line with the radius of the second line, and that gives you the total radius of the line. That is more than my poor iPad can handle. So I think it's really cool. So in other words, just by looking at this little doohickey, we found out that multiplying two complex numbers in polar form together, in order to do that, all we have to do is multiply the radiuses and then add the thetas. And that's essentially what we're doing. It's an identity of a theta, an identity of an angle to be added instead of multiplied. Because it's not really just number. It's not really just a distance. It's a tool for adding. Anyway, I think that's fascinating. I think it's really cool. But just to see this algebraically, to see it work out in the exact same way, if we were to work this out ourselves, we would get r times the cosine theta. Let's see, we get r1 cosine of theta 1 plus theta 1 plus I times the sine of theta 1 times r2 times the cosine of theta 2 plus I times the sine of theta 2. And so when you multiply these two things together, you get this. You get r1 times r2, and that then, because I've multiplied, I just took the r1 and r2 together, and I combined them together, and then I can FOIL the two things in parentheses, so that gives me cosine theta 1 times cosine of theta 2. Let's see, and then we get plus. Let's see, on the other end, if I was to just neglect the I bits for a second, actually can't really, well, if we went to the very end, if I did L first, I would get I squared, and then sine theta 1, and then sine theta 2. I know I'm doing it a little bit out of order, but I'll explain more in a second. And then I'm going to do the O and the I of FOIL. So we'll get plus, let's see, the cosine of theta 1 plus I sine theta 2, and then cosine, or not plus, this is a times, excuse me, and then times I sine theta 2 plus, let's see, I sine theta 1, and then cosine of theta 2. There we go, cosine theta 2. If you do it out of order, you might get mixed up. Okay, so here's the full schematic. So you can see, again, the radiuses get multiplied if we do this. Now let's kind of partition this up. Let's see what's going on here. The I squared, that's just negative 1. So this becomes a minus sine 2. And so sine 1, sine 2, we end up with, if you want to just focus on just this bit for a second, cosine 1, cosine 2, or cosine 1, cosine 2 minus sine 1, sine 2 of these angles. This is actually, if you remember back, I think it's 5.3. This is the identity of the addition of cosines. This is the same thing as saying cosine of theta 1 plus theta 2. That's exactly what it is. So we've got on this side radius 1 times radius 2, cosine theta 1 plus theta 2. And on the right side, we'll do the same thing. We'll look at the same thing. So actually, you'll see in both of these, we've got an I involved, so we can factor that out. We can just factor out an I from both of these. So that gives us cosine theta 1 times sine theta 2 plus sine theta 1 cosine theta 2. Now, if you're astute about this, you might notice another identity here that's helpful. This is adding cosines. That's that rule. This is actually another rule, which you may remember. This is summing sines, or in this case, finding the difference of sines. This is the sum or difference of sines. So this is subtracting. Subtracting sine. So this becomes, all of that becomes I times the sine of theta 1 minus theta 2. Great. So all together, there's a plus in the middle. So all this together, this gives us r1 r1 times r2 times the cosine of theta 1 plus theta 2 plus I times the sine of theta 1 minus theta 2. Excellent. So this is interesting because this is exactly the same as this is the exact same thing as the rule for as that we wrote up in the beginning. We said that an identity that we said we're going to define the polar form or the trigonometric form of a complex number is r times the cosine of theta plus I times the sine of theta. And we have the exact same thing here, except it's r1 times r2 times the cosine of theta 1 plus theta 2, and then I times the sine of excuse me, that's not a plus, that's a plus. This is subtracting. Did I say it's subtracting sign? Oops, I'm sorry. This is adding sign. Oops. This is adding sign. Maybe I can cut that out later. Maybe I won't be able to. I won't be able to find a way to do that well. But this is adding sign. So this is the same thing as saying r1 times r2 times the cosine of theta 1 plus theta 2 plus I times the sine of theta 1 plus theta 2. We're adding the signs. We're just adding two signs together or multiplying two signs together. That's what happens when we multiply two signs, two things together. I think it's really cool. So z1 times z2 equals exactly that. Let's make sure that's in the right color. That would go in that color. Great. Okay. So that's multiplying. Let's look at dividing and see what dividing is. And for this one, you can kind of, I won't go through the whole proof again. I mean, you can kind of get the idea, but dividing is the exact same idea. Let's actually move this to the right a little bit because I want to make sure we have enough space and that everything's lined up. I want to move this way over here. Great, just like that. Okay, so let's rewrite this. Multiply. So again, I just use sum and difference. I just use the sum and difference identities, and I used foiling, and I was able to figure this out. So great. So let's try dividing. Now, dividing is pretty much the same thing, and again, I'm not going to go through I'm not going to go through the whole process over again, just to save you time. But I encourage you. I mean, this is the same process. So it wouldn't hurt if you wanted to try to do it on your own. Actually, you don't have to do it on your own. I think you can probably get the idea from this. So this is the same thing, except instead of what'll end up happening when you FOIL it out and you do the sum of difference identities, you'll get R1 divided by R2. So let's make this difference. This is R1, and then we're going to divide by R2. And then we'll get the same thing, the cosine of theta 1, except it'll be theta 1 minus theta 2, because it's subtracting the thetas. It's doing the opposite, subtraction of theta 2. And then we're going to add to that I times the sine of theta 1 minus theta 2. So again, the exact same thing, except now instead of adding, we're going to subtract. And it kind of makes sense. If we divide things, it'll do the opposite of what we did when we multiplied it. So we're gonna divide and subtract instead of multiply and add. Okay, that's dividing. Now let's move on to the next idea. How about if we take it a step even further, and we said we wanted to find the powers. We want to find the power of it. Okay, well, if we want to find the power, if we want to raise it to a certain power, let's say we're going to take an angle z, let's say z1, or just z, for the sake of this, which is just z, and raise to the power of n. Okay, well, this is, let's see, I could do the whole thing out for you, but again, it would take it'll take a minute or two, and I think you might like to do this I think you might find the joy of doing this on your own. And again, I think you can figure this one out on your own, and I think if you do figure it out on your own, you'll be extremely satisfied when you do. I do actually, yeah, I think I would encourage you, see if you can try this one on your own to figure out why this proof is the way it is, because I mean, once you figure something out like this and you figure out this is the theorem and how this theorem becomes about, it's beautiful. And you feel awesome for being able to do it. You feel like you're a really smart, powerful person, and you are a smart person. I believe in you. I think you could actually do it. And it wouldn't take you. I think it wouldn't take too long. So here's the rule. Instead of saying normal r, we're gonna say r is now to the power of n. So again, it's kind of as we expect, except now, this is really cool. This is really cool. Now, because theta is like one step behind the normal numbers, so instead of like before we were multiplying, it was adding and subtracting. Now that we're going to powers, it's going to move up a step too, and it's going to go to multiplying. I think it's cool. So cosine of theta, and but instead of theta, we're going to multiply it by the number, the power that we're raising it to. So we'll multiply it by n times theta. So that way, theta really is, it's just one step behind the normal numbers, the linear numbers, because it's elegant. I think it's elegant. Plus I times the sine, as you're used to, of n times theta. Or you could just say n theta if you wanted to. But I'm trying to make it clear. Oops, that's not the right color. I don't know if you really care though. This is n times theta. Okay. So this has a really special name attached to it. The guy who, well, the name is coined after its actual name. It's called de Moivre's theorem. I hope I'm pronouncing that right. Maybe I shouldn't attempt to pronounce it again, just in case I get it even worse. De Moivre's theorem. It shows you how much of a layman I am. But you can just use this, just try multiplying these two things together. You can use the multiplication identity that we just found. You can use this exact multiplication identity to figure it out. And I hope you do. I really hope you do, because it's a cool one, and I think you can do it. So the next one, assuming you figured it out and you figured out the thrill of actually understanding this is the reason why it works, this power theorem. Let's go to the root theorem. The root. So this is the opposite, the root theorem. Okay, and this one might be the weirdest one of them all. And it's not that they're all weird, but it's just this one's going to be the most unique in the sense that it's going to do something that you might not expect. And I'll explain it to you after I write it down, so maybe I can help you figure out what I'm doing here. It'll start the way that you kind of expect. So if I want to take the nth root of z, the nth root of z, so I'm going to take the square root, third cube root, or whatever I want to write, whatever root I want to take, we'll start by taking that root of the radius, which makes sense. It's exactly as we'd expect. And we're going to multiply that by the cosine of theta. And here's, I'm going to put in green the weird stuff, plus 2 pi k. And we'll divide that by n. So divide that by the number we're squaring it, or the number we're rooting it by. Actually, I'll make that in dark blue as well. So it's clear that's what's changing. Okay. And then I'll add to that I times the sine of theta, the same thing. Theta plus, plus 2 pi k. And then divide that by the number we are, instead of multiplying by theta, we're going to divide by theta. And then here's a little bit of an ending. That's, again, this is the weird part. We'll have k equals 0, 1, 2, all the way up to n minus 1. Okay, what is this green stuff? So the green stuff is basically out of the idea. Maybe you remember from all the way back at the beginning when we were talking about angles. We talked about coterminal angles, angles that can end at the same point. And you'd say theta plus 2 pi. For all intents and purposes, the cosine and the sine and all of that of theta plus 2 pi is the same as the cosine and sine of theta. Or just, for all intents and purposes, they act equivalently. They act like they're the exact same. So say theta plus 2 pi basically acts, you could call it equivalent to theta. You can basically call them the same thing for all intents and purposes. At least the intents and purposes we have for the most part here. Here's where that gets weird though. You may remember that when we do roots of things, we can get into this really weird realm of extra numbers that don't normally seem to be there. And like for example, if I want to take the square root of 4 That's not just 2. Not just 2 could be that. It'd be plus 2 or minus 2. So we can get these extra roots in there that aren't normally normal. And so that's what's happening here. With the roots, you can think of that. You can think that, well, yes, if we have theta plus 2 pi, normally that equals theta. And if you were to put theta plus 2 pi in any one of these other any one of these other equations, you would still get the same number. So for example, do I have my calculator? Oh, great, great, great. So if we have, let's see, which mode am I in? Am I in radian mode? I am in radian mode. Great. So if I said, I don't know, the cosine of 2, I don't know, the cosine of 2, that gives us some negative number. And if I was to add to the cosine of 2 pi, I'd get a coterminal angle and the same downward position, and we'd get the same answer. So that's great. Here's where it's weird. Now we're dividing by n. So we're not just adding 2 pi. We're taking cosine of theta, we're adding 2 pi, and now we're going to divide by n, divide by a number. That gives us two different things. So for example, if I was to do the cosine, let's see if I was to do the cosine of 2 plus 2 pi, or 2, let's say it's divided by 2. Let's divide it by 2. 2 divided by 2, that gets us one number. But if I was to do in other words, however, if I was to do the cosine of, let's see, 2 plus 2 pi, and I was to divide that by 2, so I took 2 plus 2 pi and divided that by 2, that wouldn't work. And you can probably see intuitively why that is. That gives us a completely different number. It gives us negative 0.540. So these get us different numbers. We get different answers because when we divide something by n, you're no longer adding by 2 pi. In this case, we added pi instead of 2 pi because we divided 2 pi by 2. I encourage you to play around with it if you're still confused. I think this can click in your head if you start messing around with it a little bit. But that's the idea. So the roots do a little different things. So we have to do some different things. And so in order to account for that, we got to figure out what the roots would be if the number multiplying by, if we multiply by 2 pi, and then 4 pi, and then 6 pi, and so on. So that's what's happening here. That's why we have this. However, this does give us something that's really, really interesting and really, really helpful. So normally we try to find the roots of a particular number, and finding, let's say we had a polynomial, or let's say a binomial. Let's say we had a binomial. We're trying to find the roots of this binomial as much as we can. If we had like x to the fourth plus 2x squared or something like that. I mean, this is something you could probably do in your head, perhaps, but this is, normally we'd have a really hard time doing this because there's no like straightforward, easy, here's the way to do it, and you'd be done. We have to go through this whole process. There's no equation we can just plug this into and be done with. But with this, if we can put our equations into this complex polar form, then there is an equation that we can use right over here. This tells us exactly what all the roots of anything will be with just by an equation. We can just plug numbers in and we'll have it. It's kind of like, in some ways, it's kind of like the quadratic formula, but for finding roots. It's extremely powerful if we can find it. Now here's the question. What's up with this k stuff on the right? So I said k is 0, 1, or 2. So we could start with, when k is 0, it starts with just 0. We're just dealing with just theta divided by n. But if we had if k equals 1, then we'd have theta plus 2 pi. If k equals 2, if k is 2, then it'd be theta plus 4 pi. If it was, and k equals 1, it would be theta plus 2 pi, and so on. And we want to keep adding until we have all the roots. Now you know that the number, this n, you might remember that the n signifies, we can tell how many roots there are by the number itself. So if we take the cube root of something, there are three roots of it, in a sense. So in the same way, we can find all 3 roots just by doing this method here. Okay, so there's a lot that I covered there. It's probably, I don't have my my sand timer here with me today. I wish you did, but it's probably time for a break. So we're going to take just a really quick break, and then we're going to come back and finish up this last little bit here. Welcome back. I hope you had a few minutes to really enjoy the nature of this rooting ability that you now have. Okay, now I'm gonna blow your mind in a whole new way. I think this is, if you think that was cool, this is incredibly cool. So check this out. So I'm gonna go to right here, get some more space. Here's the idea. I wanna ask a question here once I make a partition. And here's my question that I wanna ask. Here's the question. What multiplies, here we go, ready? 2, 1. You think you got it? Right? It's 1, right? It's 1 multiplies to 1. No, so many things multiply 1 to 1. Everything, not everything, but just about, it feels like just about everything multiplies to 1. There's an incredible amount of things that multiply to 1. And it seems unintuitive at first, but let's break it down to see what I mean. Let's go this direction first. Let's see this. So you know, of course, and of course you do. You know that let's see, if I wanted to take the square root of, I just want to say, well, 1's obviously going to be a factor of 1, but you might also notice, if you're really thinking about it, there's the square root of 1, right, as well. The square root of 1, what is the square root of 1? It's not just 1, is it? It's 1 and -1. There's 2 roots to the square root of 1. And in fact, the fact there's a 2 here, like we said before, shows that there are 2 roots to it. There's a 1 and a -1. I'm going to skip 3 for a second. Let's look at 4. Let's find the 4th root of 1. Well, we know, of course, there's 1. And then we know there's -1. -1, so -1 times -1 times -1 times -1, at 4 times, is also 4. But there's also something else that you want to be aware of. And you might, if you're thinking very, very carefully, now that we're back in the complex numbers, you might even be able to figure this out on your own. And you might, if we mentioned it once before, a long time ago, something to the 4th power equals 1. I wonder if you remember it. Here it is. It's I to the 4th power equals 1. Remember, because I equals square root of -1, I squared equals 1. Sorry, that equals -1. I cubed equals negative square root of -1, and I to the 4th is 1. So we also have I here. I don't need to get into the last one, but I just want to point out that there's a bunch of complex roots of things that we don't normally think about, that we don't normally go into when we talk about prime numbers and trying to find the square root of a prime number or something like that. Well, the reason why it's prime is because there are no numbers, there's no natural numbers that can multiply up to it. But we could find some fractions that'll multiply up to it. We could also find imaginary numbers that'll multiply up to it. And that's what I'm trying to get to here. There's the 4th root of 1. There are discrete numbers that will multiply. There's imaginary numbers that will multiply to 1. And this shows us exactly how to get there. To find out exactly how many roots, to find out exactly what the roots are, we can use the same rule this really, really powerful rooting tool that we just got, this root here. We can use that same rooting tool to find out all the roots of 1. Let's actually see if we can figure it out. So let's say we want to find the 4th root of 1. We could say no, actually let's do the general thing first, and then you can skip ahead if you don't want to watch the rest. That's fine. Let's do that. So the general rule is n root of r cosine of all that junk. So we'll start with this. We'll say it's n. So the n roots of 1 equals the n root of r times the cosine of theta plus, let's say cosine of theta plus 2 pi k all over n plus I times the sine of pi, sorry, not pi, theta plus 2 pi k all over n. And I believe, is that all of it? I'm pretty sure it is. Yeah, and then we have that k thing, the k and ending. So then we have k, let's see, equals 0, 1, 2, all the way to n minus 1. Now, here's the thing. We are trying to find the root of 1, the square, the end root, not the square root, just any, but the nth root. Now let's think about what 1 is, especially on the complex plane. If we were to put this on the complex plane, let's draw a little complex graph here, and we'd say, well, if we were to graph 1, that would be, let's see, 1 equals, let's see, 1 equals, let's see, 1 plus 0i. So if we were to graph it on the complex plane, we would get that right here. Right there, 1 plus 0i. Okay, so if we want to write this in polar form, we could write this, if we could write something as simple as this in polar form, we could say the radius is, well, that's the radius is 1, and theta equals 0. That's really important. It's very helpful. We'll get to that in just a second here, and it'll get us to some cool places. Well, actually, no, we can work with this. We can work with this. So if we want to find the nth root of 1, what this means is we want to find the nth root of 1. Let's use an orange color. We're going to find nth roots of 1. I'm finding the nth root of 1 plus 0i, which is also the same thing as saying nth root of 1 times the cosine, because we can turn this trigonometric form into a, not trigonometric form, we can turn this rectangular form into a polar form, or trigonometric form. So this would be 1 times the cosine of let's see, that'd be the cosine of 0 plus I times the sine of 0 times the sine of 0. And then because of that theta and yeah, because theta and what's going on, we're going to dividing by n. But here's what this ends up as. So well actually let's break this down for a second. If we're finding this here specifically, this is not theta, this is 0. If we're trying to find the root of this, remember how we find the square root. We say to find the square root of this, it becomes, let's see, the 1's the radius, 0 is theta, so we get the nth root. Let's kind of go back to purple here to kind of say this is a continuation of the last thing. We get the nth roots of 1 because 1 is our radius, and then we have times the cosine of 0 plus 2 pi k over n plus I times the sine of 0 plus 2 pi k over n, and then we have let's see, oh, it's all in parentheses. Then we'd say that this is k equals 0, 1, 2, and all the way to n minus 1. So this is the nth root of 1. Now before I go any further and simplify this, I want you to notice something just incredibly beautiful that's right here. It's amazing, it's astounding, and I love it, and I think you should love it too. Here's what it's saying. Okay, so if we want to find the nth root of 1, we start with the nth root of 1, and then we multiply that by the cosine of all this stuff plus the I times the sine of all this stuff. But check this out, the nth root of 1, to find the definition of what nth root of 1 is, nth root of 1 is inside that definition. It's inside it. So if I want to find this nth root of 1, I could take this and say this itself would be nth root of 1 times the cosine of 0 plus 2 pi k over n plus I times the sine of 0 plus 2 pi k over n. And then we'll take all of that, and I want to say, okay, I want to find that. So all that becomes that big monster, and I want to figure out, okay, what's the nth one of this? I go down here, and that I can extend that. So this can become an infinitely large problem. It can be huge. because it recurs inside of itself. It happens over and over and over and over again. I think that's so cool. But you think this would run away? This would be impossible. This wouldn't work because this would go out of the way, and this becomes an infinite large problem, and we just can't solve it that way because it happens over and over and over again before we can solve it. But check this out. So I find out you want to find any root of 1, right? So you can find, that no matter what number you're going with, if it's the 3rd root, if it's the 5th root of 1, if it's the 90th root of 1, 1 will always be a root. It will always be a root. So this is always going to be at least 1. This is always going to be at least 1, but it might be a bunch of other things. There's like 90 other things. There's going to be 5 other, 4, well, the 90th root of 1 will have 89 other things. The 5th root of 1 will have 4 other things. But 1 is going to be one of them. 1 is going to definitely be one of them. I can always use 1. So, what this means is instead of writing the nth root of 1, it solves itself, because at any time, if I need to get rid of 1 so that I can actually solve the problem, I can say, well, I know what one of the nth roots of 1 is. I can say one of them is just 1. And then I can just solve the rest of the problem, and I can find a root. I think that's cool. And so you can take that, and then you can change, but you can put any number you want to here. So if you find another root, so if you're dealing with, say, the square root of 1, if you're trying to find the square root of 1, you know one of the roots of the square root of 1 is -1. So you could put in -1 here and use that to find another root. So you could find, oh man, you could use 1 times all this, and this will give you 1 root. So all this, that means that 1 times all this, 1 times, let's see, okay, so this is a 1 here. This means that 1 times all of this is just 1 root. But if you have 1 times anything, it's essentially the same thing as just saying, neglecting the 1 itself. So you could say, in essence, that you can get rid of that 1 and say it's just this stuff, because 1 times anything else is 1 times it is still itself. So that is one of the roots. This right here, this is one of the roots, but you can multiply that by this, which is another root, and you can get, and that is a definite way to get a 3rd root. So if you have 1 root times another root, you will always get a 3rd root. And I think that's amazing. That's really cool. That's really, really cool. I think I look at this and I'm like, this is one of those beautiful secrets, or beautiful just things that is kind of like, it's not to the same depth of e to the I pi equals 1, but it's so cool. And it's not even like, math doesn't brag about itself. It just kind of is there. It's kind of how like God just doesn't brag about himself. He's just kind of there, and he's all like, well, I'm here. And if you actually took the time to know me, you'd know I'm worth worshiping with all of my life, with all your life. It's the same thing with this. Like you look at this and you're like, well, it marks the image of God, because it's like you look at it and you're like, man, it's not bragging at all. It's just there. But you look at this and you gotta say that is cool. I think you gotta say that's cool. So anyway, all that aside, I'm moving on. This is something you would never get in a textbook, I think. But you can, because the nth root of 1 can always be 1, we can just say, for all intents and purposes, for now, we can just consider that to be 1 for now. And we'll just leave it at that. So the textbook will continue and just negate that and say that is 1, because we can reduce that to 1, instead of putting in another root. And then it'll say the nth root of 1 equals the cosine, which I think it's just sad that we have to do that, because it's such a beautiful thing. Cosine of 0 plus 2 pi k over n. So we can take the 0 plus 2 pi k, that's just 2 pi k. So this is cosine of 2 pi k over n, and then plus I times the sine of 2 pi k over n. And then we have k equals 0, 1, 2, all the way to n minus 1. That way, the reason why we use n minus 1 is that way we will make sure that we use exactly n numbers. So if there's 3 roots, we'll go up to 2. It'll 0, 1, 2. That's 3 roots, because you count 0. 0 counts as an extra. Okay. So this, in essence, this becomes our definition. This becomes a definition of the root of any root of 1. So if you run this a bunch of times, enough times, and you will get all the possible roots of 1. And I think we will find an example of this in one of the homework problems. So I'm gonna let you, well, when you get to that homework problem, I'm gonna help you do that one, and we'll walk through what this looks like practically. But for now, that's the last of the ideas, it's last of the work. So I'm gonna leave you there. If you want to do the homework on your own, great. I'm gonna publish another video pretty right after this with the homework problems. So I'll see you there.